This is Dr. Mitch Robinson, and this video is on the metabolism of fructose and galactose, and it accompanies handout number 8 for cellular and molecular medicine. In this video, we'll examine the cellular metabolism of fructose and galactose, and we'll look at some clinical conditions that come about due to inherited deficiencies in the enzymes necessary for their metabolism. As we've seen, both monosaccharides are significant components of our diet. Fructose is present in the disaccharide sucrose, and it has become increasingly common in foods with the manufacture and use of high fructose corn syrup. Galactose is found primarily in milk and dairy products in the disaccharide lactose. The figure on the second page of your handout shows the entry of galactose in green and the entry of fructose in blue into the pathway for the metabolism of glucose. Now on page 3, we begin with the pathway for fructose metabolism. In order to metabolize fructose or galactose, we need to convert the monosaccharides to an intermediate in the pathway for glucose metabolism. For fructose, there are two ways to do this. Remember that hexokinase, which phosphorylated glucose in tissues other than the liver, can phosphorylate other monosaccharides, and this includes fructose. So in non-hepatic tissues, fructose can be converted to fructose 6-phosphate by hexokinase. In the liver, glucokinase is specific for glucose and cannot phosphorylate fructose. So we need an additional enzyme in the liver, fructokinase. Fructokinase phosphorylates fructose at carbon 1 rather than carbon 6. Most of the fructose in the diet is metabolized in the liver, not in peripheral tissues. So this is the predominant route for fructose metabolism. In glycolysis, we make fructose 1,6-bisphosphate and split the molecule to 2 triose phosphates. But in fructose metabolism, instead we split fructose 1-phosphate. And this is a special aldolase enzyme called fructose 1-phosphate aldolase, or aldolase B. The product is dihydroxyacetone phosphate and glyceraldehyde rather than glyceraldehyde phosphate. There is an enzyme triose kinase that can phosphorylate glyceraldehyde to glyceraldehyde 3-phosphate. So now we have the two normal products of glycolysis. So a few things to recall about fructose metabolism. It's metabolized by fructokinase in the liver, hexokinase in other tissues. It's phosphorylated at carbon 1 in the liver, carbon 6 in other tissues. And remember the three enzymes that we need in the liver: fructokinase, aldolase B, and triose kinase. Although the metabolism of fructose takes a somewhat different route in liver and other tissues, it yields the same net energy as glucose. Importantly, this route bypasses the phosphofructokinase step, and remember that this is the main control point in glycolysis. The result is that fructose metabolism is not well regulated, and there's a very high rate of metabolism in the liver. Now, we've been looking at glycolysis as mainly an energy-producing pathway, and that's the case in most tissues other than the liver. But in liver, much of the pyruvate that is produced in glycolysis is converted to acetyl-CoA and used to make fatty acids. The fatty acids are eventually exported as triglycerides to adipose tissue. So glycolysis can be an anabolic pathway in the liver when it's used to convert dietary carbohydrates to fat. So looking at the metabolic pathway for fructose metabolism gives us an understanding of why the increasing amount of fructose in the diet is a problem. This sugar is metabolized predominantly by the liver, and it goes through a different pathway, one that is not well regulated and which can result in the synthesis of fatty acids for storage as triglycerides. There are two enzymes in the pathway for fructose metabolism in liver that can be defective and lead to metabolic disease. The first is essential fructosuria, and it results from a deficiency in fructokinase. This is a rare disease and it's fairly benign, marked only by the presence of fructose in the urine. There are no other clinical symptoms. Fructose is not metabolized by the liver, so it's either excreted, unchanged, in the urine, or it's metabolized by hexokinase in adipose tissue and muscle. A deficiency of aldolase B results in hereditary fructose intolerance. The block at aldolase B causes accumulation of fructose 1-phosphate. The symptoms include vomiting, hypoglycemia, and jaundice. The accumulation of fructose 1-phosphate eventually leads to depletion of phosphate in the liver, and this leads to low levels of ATP. Glycogen breakdown and gluconeogenesis are inhibited by the lack of phosphate, and this results in hypoglycemia. Now, this disorder is usually first seen as infants move from breastfeeding to ingesting fruits and fruit juices. It can be fatal if not diagnosed early on, but if a diagnosis is made, it can be effectively managed by eliminating fructose from the diet. We get galactose in the diet primarily from lactose in milk and dairy products, and we metabolize it mainly in the liver. Recall that galactose is the 4-epimer of glucose. It can be converted to glucose, but only when it's in the activated form, UDP galactose. This is UDP galactose. It's galactose linked to uridine diphosphate. The pathway for galactose metabolism in the liver begins with galactokinase. And like fructokinase, it phosphorylates at carbon 1. And the product is galactose 1-phosphate. The galactose 1-phosphate is then converted to UDP galactose. And the enzyme uses UDP glucose as a donor of uridyl phosphate. So here we can see that the uridyl transferase just exchanges the uridine diphosphate of UDP glucose with the phosphate of galactose 1-phosphate. And this gives glucose 1-phosphate and UDP galactose. Now that we have UDP galactose, we can epimerize the galactose moiety to make glucose. And we get back UDP glucose, which can be used again by the transferase. So the net result is the conversion of one molecule of galactose 1-phosphate to one molecule of glucose 1-phosphate. Glucose 1-phosphate can be converted to the glycolysis intermediate glucose 6-phosphate by phosphoglucomutase. There are inherited disorders of galactose metabolism that lead to serious metabolic disease. Galactokinase deficiency is a rare disorder that results in elevated blood galactose. It's sometimes referred to as non-classical galactosemia. The main symptoms are galactose accumulation in blood and urine and cataracts that are caused by a metabolite of galactose, galactitol. I'll talk about galactitol a bit later. Classical galactosemia is due to a defect in the transferase enzyme, galactose 1-phosphate uridyl transferase. This disease is sometimes referred to as GALT or galactose transferase deficiency. In this disease, galactose and galactose 1-phosphate accumulate after ingestion of milk or other lactose-containing foods. Infants with the disease develop symptoms soon after birth, including vomiting, diarrhea, and enlargement of the liver. Jaundice is common, sometimes progressing to cirrhosis. Cataracts will form, and if galactose is not eliminated from the diet, mental development is soon affected. We'll go into more detail on classical galactosemia in our group exercise. There may also be a defect in the epimerase enzyme, but this is a very rare disease, and in most all cases observed, only erythrocytes have been affected. Most people that have had this disorder have normal growth and development. In both classical and non-classical galactosemia, levels of galactose become elevated in the blood, and cataracts can result when galactose is converted to galactitol. The enzyme that does this is aldose reductase. Aldose reductase converts sugars, particularly aldohexoses, from an aldehyde form to an alcohol form by reduction using NADPH. Galactitol is less soluble than galactose, and it can precipitate from solution and cause tissue damage. This also causes water to diffuse back into the lens of the eye. This together leads to clouding of the lens or cataract formation. Okay, so that completes our video on galactose and fructose metabolism.